Oh, that's the week we come back from break. Wait.
All right, we are going to wrap up this last section of Unit 2 today on page 162. And before we get started, just want to give you heads up with our schedule. I can find my marker. Oh, no. That's up there so we know what's happening when we get back.
Can we just take the test on Thursday?
No one's going to be here.
Well, not this Thursday, next Thursday.
No.
On Thanksgiving?
No, he said next Thursday, I think.
Yes.
So we're going to wrap up Unit 2 today. Tomorrow is going to be our free response day. Wednesday is going to be our review day, even though we're going to be in here for like 20 or 30 minutes for the half day. Which means the day we come back from break, we're going to have our test. Okay? Make sure that you look at it every day. 15 minutes, 10 minutes, 20 minutes, something. Okay? Don't let it go to the wayside. Okay? Don't forget it. A little bit every day. That's all you need to do. And then what else is Tuesday when we get back? Homework. Okay, yes. Homework is due. So make sure that you complete that over break as well. All right? Anything about that schedule? No? I know the timing stinks, but that's just how it's working out. Okay? I apologize for that, but it's kind of out of my hands. We're going to take a look on page 162. We were looking at polynomial functions on Friday and exploring the end behavior a little bit more, how we can relate that characteristic to an equation. So we're going to take a look at another table example like we left off with on Friday, and then we're going to get into what I think are some more advanced type analysis problems where we are going to officially graph polynomial functions by hand without a calculator. So we're going to identify some of these different characteristics we've been talking about, and we're going to use those to our advantage to graph. Now, the graphs that we draw are not going to be very accurate. Okay, they'll be accurate to a point, but we're just going to get a rough general shape as to what these graphs look like. Okay, we're not going to get very specific in terms of detailed points. So on page 162, let's take a look at this table. The table below shows a function of a polynomial. The zeros are the only zeros in the table, and no zero has a multiplicity greater than 2. All right, use that information in the table to help you with the questions. Identify the left and right end behavior. Can we tell based off the graph how the ends are acting? We used phrases like rise and fall on Friday when we listed or completed that detailed chart, so maybe we can use those here. Can we determine whether we rise or fall on the left or right hand sides? What do you see, Travis? Yeah? Left is rise. How'd you know?
The x's are going negative u of x's are going positive.
Okay, so as the x's get negative, meaning going towards the left, notice how the y's are getting positive, so you're going up. Okay, you're rising. What about the right end behavior? If we're going towards the right, what are the x's doing? They're getting larger. All right, so as the x's get larger, what are the y's doing? They're getting larger. Okay, going up. So right-hand side would be rise as well. Good. All right, so based off the end behavior that we identified in the table, let's see if we can relate that to what the actual equation of this polynomial function might include. So can we relate end behavior to the degree of the function and the leading coefficient? This is kind of the big thing from the chart that we did on Friday. We were trying to find a pattern or a connection between these different characteristics. What do we think? Go ahead, Hadley. Even degree. How'd you know? Okay, so same end behavior. Okay, even means end behavior goes both up or both down. Okay, same end behavior. What about leading coefficient? Do we have a positive sign out front or a negative sign out front? How can we tell? Good, Alicia? There we go. Positive because right side or end behavior rises. Looks good. All right, looking at the table a little bit further, can we identify the zeros, the x-intercepts? They said that the ones in the table are the only ones, so there aren't any hidden x-intercepts that we got to worry about. Can we list where they are? Good, yeah. Because, how'd you know? Y values are 0. All right, so looking at the table, we can identify those points. Good. But they also want us to figure out multiplicities. So can we look at the table a little bit more to figure out what the behavior of the graph looks like at those particular spots? Can we determine if we go straight through, if we bounce, if we're level? The numbers are telling a story, yeah.
Okay, so -3 has multiplicity too.
How'd you know?
Because the y values on the left and the right are both positive. They by meaning and bounced off the x.
Okay, so notice how left and right are both positive. So that means you're not going through the x-axis, therefore you must be bouncing. So we'll say no sign change. Okay, between the y values, they stay positive on both sides. What about for -1 or 2? Good, Caitlin? Yeah. Okay, because there is a sign change. How'd you know it wasn't a possibility of 3? Can't be greater than 2. Okay, so if you read the directions at the top, they're kind of cluing you into that's not a possibility. So there's no leveling, it must be a 1. Yeah.
But, like, if that wasn't true, like, if it didn't say that it couldn't be greater than 2,
then
how would you be able to differentiate?
You couldn't.
Okay.
You couldn't. We would need very, very close, we would need like 1.9 and 2.01 to see if those are really close together, to see if it's a level.
Okay.
But if it did not say that, you couldn't make that conclusion. All right, good question. How are we doing so far? Okay, we're going to bring this together and write the equation, so the exact equation for this table. And we're going to use some of the information that we've already listed in parts A, B, and C to help us out. But like we saw on Friday, we might have to do kind of an extra thing to figure out a particular piece of this equation. So let's see, if we start with the x-intercepts, we can go ahead and write their related factors. And since we already listed the multiplicities, we can show those in the equation by writing them as the appropriate power on the factor. So we'll have 2, 1, and 1. You don't have to write the multiplicities of 1 there, okay? If you do, just as a reminder, that's okay. Now, in order to figure out the exact equation, we said that we need a positive leading coefficient. So we're going to go ahead and just write a positive A out front. We're not sure if this should be 2, if this should be 10, if it should be 1.5. Okay, it's just some positive number. but it's our goal for this particular question to figure out what is that number. So how do you want to go about trying to figure out what A is? How can we figure out this leading coefficient? Go, Caitlin. Plug in numbers for x and y. Okay, so you have a bunch of options based off the table. Caitlin, do you have a preference as to which one we choose?
4 and 490.
Okay, good. Try to pick one that doesn't have any decimals, because I know you're going to like that one better. And just as a reminder, you cannot choose one of the x-intercepts, because if you were to plug that in, the whole thing would become 0, aka the a would not be there anymore. So you have to pick something other than an x-intercept. Let's plug in 490 for our y value and 4 for the x's. All right, so 7 squared times 5 times 2. 5 times 2 is 10, times 49, 490. A is conveniently 1. Was that our A value from Friday? Yeah? Okay. It's not always going to be 1. Let's not make that assumption, okay, or conclusion. It most likely is going to be something other than 1. For some reason, it just worked out nice for both of these examples. So g of x, bless you, is 1 times x plus 3 squared times x plus 1 times x minus 2. Okay, there's the exact equation that would produce that table of values. All right, I think that was a good review from Friday. What we're going to spend the rest of today looking at, though, is trying to graph polynomials by hand without using a graphing calculator to help us. So we're going to pick apart, analyze different equations, try to figure out some of these characteristics. Notice how if we can figure out multiplicities and x-intercepts, we know those are particular spots on a graph. Maybe we can use end behavior to help us determine what the ends of the graph look like. So we're going to try to bring all this together and graph these polynomials by hand. Taking a look at this first one, if we were to try to figure out the x-intercepts, how would you want to do that? Yeah? Factor. Okay, so take a look. Think of your techniques. How can we try to factor? Yeah? GCF. Okay, so what do you want to take out?
2x.
A 2x? Okay, how about, can we make it a negative 2?
Yeah.
Okay, so we'll take out a negative 2x. We're left with x squared plus 4x plus 4. So we're done with GCF, but ask yourself, can you keep going? The leftover kind of looks like I am factoring. Can we think of two numbers that multiply to 4 but also add to 4? Yep. 2 and 2. All right, so x plus 2, x plus 2. Now, I highly suggest if you see 2 or 3 or 4, whatever number, if you see the same factor written multiple times, that's cluing you into a multiplicity, okay, multiple times, multiplicity. So we're going to go ahead and put this as a power of 2 on that factor. So it looks like our x-intercepts are 0 and negative 2, okay, based off that lonely x out front and the x plus 2 factor. And let's go ahead and list their related multiplicity. Notice how the power on the x out front is 1, and the power on the x plus 2 factor is 2. Okay, so factoring is going to lead us into x-intercepts and multiplicities. Now that we have those, let's go ahead and graph them. So we can put a dot at the origin and a dot at -2. So we know those are two specific points on the graph, and the multiplicities are also leading us into how the graph is behaving at those spots. For instance, at -2, we know the graph should be bouncing, but we're not exactly sure if it's bouncing up or bouncing down. So we have a little bit more information to kind of pick apart from this equation to help us determine which direction the graph is kind of moving in, and that's where the end behavior is going to help us out. So if you look at your equation, finding the highest powered term, okay, is going to help us figure out that degree and leading coefficient. So let's see, I'll write this at the bottom. Our degree is x to the third, and looks like our leading coefficient is a -2. All right, so I'll write negative. Can we determine our end behavior? What's happening on the left and the right hand side? Can we use fall and rise as some description or descriptors? If the leading coefficient is negative, what do we know? Go ahead, Alicia. Right end behavior falls. Okay, so I'm going to put a little arrow on the right-hand side that's going down. And if the degree is odd, we know that the other side, in this case the left-hand side, should be opposite. So it will be going up. All right, so I put in little arrows as guides there. So somehow we have to draw a graph that goes up on the left, down on the right, bounces at -2, and goes straight through at the origin. So we got to bring all of that together. What I suggest is drawing your graph from left to right, just like you would read a book. So on the left-hand side, I'm going to start at the top because that's what the end behavior is signifying. And I'm going to come down and connect to my first x-intercept. Now at this spot, we said we have a multiplicity of 2, so we should be bouncing. That means we're going to bounce back up. But then we need to connect to the other x-intercept because we know that's a specific point on the graph. At this x-intercept, if it's a multiplicity of 1, I should be going straight through. And since that's the last x-intercept we have, there's no other point to connect it to. It should match the right end behavior that you listed. And notice how it's going down. So there is a rough sketch as to what this polynomial graph would look like. Notice how there are no tick marks on the y-axis. We are not getting specific enough to say the height of all these different humps that we have, but it's just a general shape of the graph. Okay, we specifically have x-intercept points, but the heights are a little unknown. We have to dig a little bit more into that, but at least it's a general shape. All right, let's try the next one. Factoring technique to help us find the x-intercepts. Grouping, we have 4 terms. All right, out of the first group, x squared. What can we take out of the second group so it matches a 2x plus 3? -9. Good. All right, so grouping gives us x squared minus 9, 2x plus 3. We're done with grouping, but you got to ask yourself, can you keep going? Do we see the difference of squares for the x minus 9? All right, so x plus 3, x minus 3, and then 2x plus 3. Let's go ahead and list x-intercepts and multiplicities. So x-intercepts are -3, +3, and -3/2. None of those factors show up more than once, so all their multiplicities must be 1. All right, so we'll plot those. Negative 3.5, or sorry, 3/2 is the same as negative 1.5. Let's look at the equation a little bit more to help us with the end behavior. If you find the highest powered term, it looks like for this case our degree is a 3 and our leading coefficient is a 2, which is positive. So positive leading coefficient means the right-hand side rises. So we'll draw a little arrow. And since we have an odd degree, the left-hand side has to do the opposite. So it'll fall. All right, so all these multiplicities are 1. When we trace and connect our dots, we need to be going straight through. So on the left-hand side, I'm going to start at the bottom, because that's where the end behavior is telling me I should be. And I'm going to play connect the dots, going straight through the x-axis for every single one. And notice how it matches the right-hand side end behavior. All right, so there's a rough sketch for that graph. We hanging in there? We're going to switch things up a bit. The next ones, yeah. Yeah. These next few are going to be a little bit nicer because they're already factored for us, so we don't have to do that extra step to help us find the x-intercepts. We should actually be able to go straight there with these examples. So if we list x and multiplicity, we'll get -2, 1, and 3. Notice how none of the factors are written more than once or have powers other than 1. So all the multiplicities are 1. Now what might be a little bit different for this case is trying to figure out what the degree and the leading coefficient would be. Now we got to think about if we were to actually multiply all these factors together, okay, get it in standard form, what would that highest powered be, and also what would the number out front be for that term? So I suggest taking a look at a combination of the x-intercepts and the multiplicities. Notice how this first factor has an x to the first term in it, and we're multiplying another factor that has an x to the first, and we're multiplying another factor that has an x to the first. I'm only looking at the x's because I'm trying to find the highest x power. Okay, if we kept multiplying, we'd have other x powers, but they would be lower. So if we did x to the first times x to the first times x to the first, we would get x to the third. Okay, specifically 1x to the third. So notice how the degree is odd, and if the number out front is 1, in this case, that would be a positive leading coefficient. So let's try to draw this graph. We can go ahead and plot the x-intercepts. Positive leading coefficient, right side is going to go up. If we have an odd degree, the left-hand side is going to go down. So we have to follow the end behavior, playing connect the dots, and each x-intercept we're going to go straight through based off the multiplicity. So it looks like something like that. So it kind of looks like we have a trade-off. Instead of needing to factor for these examples, we have to do a little figuring as to what the degree would be. Okay, so it's a little give and take there. Let's go and try the next one. X and multiplicities. So based off the factors, -1 and 2 are the x-intercepts. Looking at the related powers, looks like we'll have a multiplicity of 2 for our first factor, and then 1 for the second. Let's see if we can get the degree and leading coefficient to help us with the end behavior. So for our first factor, we have an x squared, and we're multiplying that by an x to the first in the other factor. So if we actually were to multiply all these factors together, we would end up with a 1x to the third as the highest power. There are other terms, but we just want to figure out the highest one. So we have an odd degree, and coefficient out front is 1, so that is positive. Looks like right-hand side will go up, left-hand side goes down. We have to play connect the dots, following the end behavior, but notice how we have to bounce at -1, because the multiplicity we said was 2. All right, so it might look something like that. We bounce at -1, and we go straight through at 2. Do you guys think you can try the next 2? No? Yes?
We're good.
We're okay? Try the next 2. We're going to do the last 2 together, but go ahead and try the next 2.
Can you give me a word problem that we use for one of these?
Multiplicities? Or like just drawing?
Like a graph, what situation would a word problem be used for? Think a graph.
If you can think of some scenario that would be modeled by a connected function.
Yeah, like what would this scenario be? Like when, or in what situation would you need something to fit the power?
If you want to model sales or something, like if you have, like you know how the stock market goes like up and down, up and down. So if you have a bunch of, I mean it's more jagged.
But so if you have
That's
it,
just
that's
that's a bunch of random points. It's not actually following.
I mean, like,
No, but you can plot those points in your calculator and you can figure out the regression model that would model it.
so like you'd be able to.
If you wanted to predict data, you could do that.
I guess it would help a little bit.
Yeah. So you're right, they are random points, but if you wanted to predict the trend of something,
So like stats.
you could turn it into an equation and it might be quantitative. Like the best equation that would fit that data might be a power.
No.
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 Well, no, it's just gonna be like a bunch of random numbers.
Well, maybe it models into a point. Like you can
Yes,
say
I
a
know.
predictive function is only accurate up to a certain point, you know?
Is there
Like exponential
Yes.
functions model population growth, but there's no way populations can continue to increase forever.
I know.
So
I was just
only
saying,
good
I was
to
like, yes, no.
Yeah, it was like immediately.
Yeah.
Because it wasn't directed towards you.
Happy with this one.
She's an Excel, she definitely wants it.
Mega odd.
How do we do? We gotta check out any particular piece of those two examples.
No, I'm gonna do it. I'm using it.
She made the go we done.
Are we supposed to make it go with
It probably doesn't matter.
Say what?
For the fourth one.
Yeah?
We made it go down really far. We're supposed to make it go down that far.
Go what far? Like down?
Yeah.
Oh no. No, so I drew mine down there. Like
It just looks better that way
It does.
than
It looks
there's this is just a rough sketch. Like
Okay.
yours might only look like this.
Yeah,
Yeah.
That's fine. Okay?
No Y values, so
Right.
it can be whatever.
It could be anything. So it's just a rough sketch.
Alright.
All right? You're sure we're good? All right, we're going to check out the last two together. These are a little different. All right, let's go ahead looking at the factors. We'll list our x-intercepts. Look at this one. X plus 1 times x plus 1. X plus 1 squared. Maybe that would help. Okay, so you really have to write it once. And then our other x-intercept looks like 3. Multiplicities would be 2 and 1. All right, I'm going to go down here, try to find degree and leading coefficient. So looking at our powers now, we have an x squared times, what's going on in this other factor? We have a x to the first, right? But it's negative. Okay, well if you want to divide a negative out, then it would look like this then. That's fine too. Right? So regardless, you'll get a negative x to the third in the end. Whether you want to count the negative here or you want to factor it out, doesn't matter. So our leading coefficient is negative. Let's go ahead and bring our results together. So x-intercepts, look at the end behavior. The right-hand side is going to go down. Since it's an odd degree, left-hand side will go up. We need to connect the dots, making sure that we bounce at -1 and go straight through at 3. So something like that. All right. If we look at k, we're going to have something similar happening here. Notice how the middle factor is a -2x. So you could factor the negative out if you want to, or you can just include it when you do your degree calculation. Either one's fine. But let's go ahead and list our x-intercepts. So -3, and then we'll have a positive 3/2 for the middle factor, and positive 3 for the last factor. Multiplicities 1, 1, 2. All right, to calculate the degree, we have an x to the first times a -2x to the first times an x squared. So if we were to multiply everything together, our leading coefficient, or sorry, our first term rather, would be -2x to the fourth. Looks like our leading coefficient's negative. So we'll plot the x-intercepts. Leading coefficient's negative, so the right-hand side goes down. even power this time. Left-hand side will also go down. So we have to play connect the dots, making sure we go straight through, bless you, at the first 2 x-intercepts, and then we bounce at 3. So might be something like that. All right, these are just rough shapes. If you really wanted to get accurate, and you can take the time to actually graph these on your calculator, just to see the shape of the graph, but notice how we can do these without a calculator just by recognizing certain characteristics like x-intercepts, multiplicities, end behavior. We're just trying to get a gauge or a feel for what graphs can look like, okay, without needing a calculator to verify that. We doing okay? Anything else we want to take a look at? This is officially the end of Unit 2. All right. So we'll end there. Free response day tomorrow, review day Wednesday, unit tests when we get back from break.